some of the stuff that Gary wrote, I think in his attempt to be maybe simplistic or make it straightforward, some of the stuff he writes is a little bit incorrect. So we're going to finish down the pure side of the matter map. Last time we met, we went into detail, maybe a little more detail than we needed to go, about the elements, how they're arranged in the periodic table. I dictated predicting ion charge from position, which is maybe a little bit ahead of where we need to be, but suffice it to say that there is a lot of information in how we organize the elements and why, and we're going to spend an entire section and really beyond that explaining the periodic table when we get to chapter 6. Okay. Another distinction correlating with pure substances is if they're not elements, then they're compounds. And there's a number of ways to classify compounds. And you might remember in the instructions on Google Classroom, I asked you to replace the word molecular in the compound beginning, I believe, on page 73. Where you see molecular, write covalent. And I'll explain why we're going to make that change as we go through it, okay? So if we go down here to compounds, again, this is why sometimes I question how Gary's brain works. Just in case the word compound doesn't make sense to you, compound word is one word that's made from more than one word, daycare. That is an amazing revelation. A compound of matter is a pure substance composed of more than one type of atom. Now it all makes sense. This isn't a word. A compound can be decompounded. If you look that up in the dictionary, there's no word. We say decomposed, that's because that's what we call it. Okay? And you guys all know about decomposition reactions. I don't understand why he needed to do that, but in any event, single compound reacts to produce two or more new substances. That's fine. There's a decomposition reaction. Notice that what it decomposes into are elements. Here, what it decomposes into are two new compounds. Here, what it decomposes into, again, is two elements. And as you're going to learn, and if you don't remember from last year, we call it decomposition not because we make two elements, but because we start with one reactant. If there's one reactant, it's a decomposition reactant. Okay? We can classify compounds in several ways. Organic or inorganic is maybe a little bit premature. Organic chemistry is the chemistry of carbon compounds, but just because something has carbon in it doesn't mean it's organic. If we have time, and I hope we do, Chapter 8 is all about organic chemistry. Unfortunately, organic chemistry is usually relegated to a single chapter at the end of a course in grade 11. Which is unfortunate because if you go to post-secondary chemistry, certainly after first year, the vast majority of courses you'll have to pick from have the word organic in front of them. And there are more organic compounds than there are words ever invented in any language by humans since the beginning of time added together. Organic compounds outnumber inorganic compounds by more than 99%. And every year there are hundreds of thousands of brand new organic compounds synthesized over the globe. All right, so it's a massive branch of chemistry. I wouldn't worry too much about this distinction now. We'll do it in a lot more detail in Chapter 8. I think Gary gives us a table or two later on in the review questions, and I'll go through those with you, time permitting, today, okay? This little sentence, because of carbon's unique ability to form extended chain structures, that's one of its unique abilities, but it has several that are unique in the chemical world, and life is based firmly on that element. But it's not just extended chain structures, it's more complicated than that. Countless billions of carbon compounds? I don't know if I'd say countless billions. Well, there are less than 1,000 inorganic compounds. Organic compounds are effectively covalent. And covalent compounds, as we're going to see, are made of non-metals like other non-metals. So you might think if there's only this few non-metals and that many metals, you would think that there would probably be more inorganic compounds than organic, but that's not true at all, not even close. And part of the challenge of organic chemistry is actually classifying those millions and millions of compounds. And to do it, organic chemistry had to invent a whole new language for naming these things. Because if you think about it, if the number of organic compounds outnumbers every word in every language added together since the beginning of time, it's kind of a challenge to say, I want a name that's unique to every compound. And it effectively meant inventing a new language. And that's one of the things we're going to talk about in Chapter 8. Another way we could distinguish compounds is binary versus non-binary. Binary means two different elements. So water's a binary compound, hydrogen and oxygen. Sodium chloride's a binary compound. But if there's more than two elements, and I mean there has to be different elements if it's a compound. If there's more than two elements, it's not binary. So calcium carbonate, calcium, carbon, and oxygen. And there's names that we give to non-binary compounds. If it's a three-element compound, there's a term we use called ternary. You don't have to remember that. If there's four elements, it's quaternary. Gary is just another way to do it, okay? Kind of like people that are Irish or people that they wish they were, that type of thing, right? Now this is where I differ from Gary. Ionic compounds versus covalent. The reason I want you to change that is because what Gary would have you believe is if the bonding is covalent, then the compound exists as individual molecules. For the most part, that's true. And this is a great example. Water is a covalent molecular compound. The bonding is covalent, and the compound exists as individual neutral molecules. But just because the bonding is covalent doesn't mean neutral molecules exist. And I'll explain why that is in a few minutes. You guys all know that an ion is a charged atom or group of atoms. Compounds made from individual ions are called ionic compounds. And ionic compounds are held together by a three-dimensional network of ionic bonds that hold all of the ions together in a regular arrangement of those ions called crystal lattices. So for example, there is an example of a sodium chloride crystal lattice. Crystallographers, which are chemists that study crystals, have designations for how the ions pack. So there's things called face-centered cubic, body-centered cubic, a whole array of how ions combine in a crystal lattice, depending on how big they are relative to each other and depending on the ratio, okay? But when I write the formula for an ionic compound, the formula that I write does not represent a molecule. So when I write NaCl, it's not true to say, well, that's a molecule. It isn't. Molecule is a neutral independent species. All that represents is a ratio. And that means this is worth writing down. So write this down. In ionic compounds, no neutral independent molecules exist. In ionic compounds, no neutral independent molecules exist, like as in the case of water. The formulas that we write for ionic compounds, can I write this down, Kim? The formulas that we write for ionic compounds simply represent the smallest whole number, or integral if you want, ratios. The formulas that we write for ionic compounds simply represent the smallest whole number ratios of cations to anions, that's positive to negative ions, of cations to anions that are electrically neutral. So from the top. In ionic compounds, no neutral independent molecules exist. The formulas that we write for ionic compounds simply represent the smallest whole number ratios of cations to anions that are electrically neutral. So all that means is, in this crystal lattice, there's one sodium ion for every one chloride ion. So what do we call that? We don't call it a molecule. We call it a formula unit. The smallest unit of the formula that's neutral. Okay. Now obviously, if the charge on a sodium ion was 2 plus, and the chloride is 1 minus, then the ratio would be 1 to 2. Magnesium chloride is an example of that, MgCl2. That means for every one magnesium cation, there are 2 chloride anions. If you look at your table of ions once again, backside of the second last page in the book, and again, it's, from here on in, you're going to get that on every test you get. You don't have to memorize all of it. But notice a couple things. Notice that when we write the charge for something that's bigger than 1, whether it's negative or positive, we put the number in front of the sign. So for example, oxide isn't -2, it's 2 minus. Aluminum isn't +3, it's 3 plus. So the number goes in front of the sign. Is there ever a case where the sign goes in front of the number? There is, but it's not an ion charge. It's something we refer to as an oxidation state. And that's something we'll talk about in chapter 4. But when you're indicating ion charges, put the number in front of the charge. And they do it for you in the book. Something else to notice. Some of the ions have more than one atom. And that's why we call them polyatomic ions. Notice that the vast majority of polyatomic ions are negative. So if you look in the top part, there's 3 polyatomic ions listed there that are positive. One of them is ammonium, NH4, 1 plus. Another one is hydronium, and they're listed alphabetically by name, H3O plus. And then there's one in the right-hand column called mercury 1. And it's actually 2 mercury ions stuck together, overall with a charge of 2 plus. But those are the polyatomic cations. But on the bottom, there's a whole bunch of polyatomic anions. What else do you notice about the polyatomic anions on the bottom half? What's the first thing that jumps out at you? What's common to the vast majority of the polyatomic negative ions?
They all, or most of them have oxygen.
Most of them have oxygen, yeah. Sometimes the same element is combined with different numbers of oxygen. So nitrite, nitrate, sulfite, sulfate, chromate, dichromate, chlorate. perchlorate, chlorite, hypochlorite. Yeah. Notice that something else which maybe is a little more nuanced. Most of the polyatomic ions are negative. Most of the polyatomic ions contain oxygen. But look at the formulas for the majority of polyatomic anions. Not all of them, but the majority of them don't have any metals in them. They're nonmetals, which suggests that the bonding inside those negative ions are actually covalent, which is true. So for example, chlorate, ClO3. The whole thing has a -1 charge, a 1- charge, but the bonding inside the ion is covalent, which is interesting. The electrons are being shared within the structure, but the overall thing has a charge. Same with ammonium, top of the page. Polyatomic ion, second from the top, nitrogen and hydrogen. It's got a positive charge, yet nitrogen and hydrogen are sharing electrons. Hydronium, H3O+, same thing. Electrons are being shared. Okay? And we'll talk more about that later on in the year, but it's just an interesting observation. All ionic compounds are solid at room temperature because the bonds that hold the crystal lattice together are ionic bonds extending in 3 dimensions. And the ions pack in such a way to maximize the attractive forces, minimize the repulsive forces. And you can't really tell from looking at this, but around every negative ion, there's 6 positive ions, and around every positive ion, there's 6 negative ions. So the big green ones are the chloride anions. Notice around that, in 1 dimension, we've got the positive ion to the left, right, bottom, top, but inside the lattice, there's also one in front, one in behind. So if I take a chloride anion, inside the lattice, every anion is surrounded by 6 cations. And every cation is surrounded by 6 anions. And that's how the attractive forces are maximized and the repulsive forces are minimized. Okay? And depending on the relative size of the ions and the actual spaces between them and the ratio, they pack in different ways. Okay? If you want to melt an ionic compound, all ionic compounds have very high melting points. The reason that is if you want to turn this NaCl solid into an NaCl liquid, it means that you have to break all of the ionic bonds in 3 dimensions for that crystal to collapse. And that takes a lot of energy. Table salt melts at 801 degrees Celsius. Molecular compounds, or covalent compounds, often melt at much lower temperatures. And we'll talk about that in a few minutes. Non-metal atoms can also become more stable by sharing electrons. So remember, non-metals are on the far right of the table. The easiest way for them to be like the nearest noble gas, which means having the same number of electrons in that outer shell, is to share electrons. Non-metal atoms never form cations. They never give electrons away. They'll take electrons from metals, or they'll share them with each other. If they're sharing them with each other, the bond is called a covalent bond. That makes sense? Sharing valence electrons. A neutral group of covalently bonded atoms, this is where I differ, is, let's rewrite that. A neutral group of covalently bonded atoms usually exists as neutral molecules. Usually exists as separate molecules, maybe a better way to say it. But just because the atoms are bonded covalently doesn't mean they exist as separate molecules. Most do. Most covalent compounds exist as neutral, independent molecules. And the most common example of that is water, okay? Are there any covalent compounds where the electrons are shared that kind of look like this? Are there any covalent compounds that exist as solids where the bonding in 3 dimensions is covalent rather than ionic? And the answer is yes. And that's why this is not true 100% of the time. If I want to melt table salt, I got to raise the temperature to 801 degrees Celsius. If I melt ice, 0 degrees. A lot of people make the mistake of thinking, well, if covalent compounds have low melting points, and some of them exist as liquids, some of them exist as gases, some exist as solids, that must mean that covalent bonds are weaker than ionic bonds, and that nothing could be further from the truth. So to take care of all of that stuff, if you flip ahead in your book to section 6.3, which is appropriately titled Describing Chemical Bonding, and go to the bottom of page 311. Remember that ionic compounds are all solids at room temperatures and have high melting points. This results from the vast number of interionic forces locking all the ions together in place in a crystal lattice. As mentioned earlier, the common ionic compound sodium chloride melts at 801 degrees Celsius. Consider covalent compounds, however. Usually exist as individual molecules and in any of the 3 states of matter, solid, liquid, or gas. So notice it says usually exist as individual molecules. One should not conclude from this, however, that covalent bonds are any weaker than ionic bonds. Consider, for example, the molecule methane, CH4. That's the majority of the gas that comes out of these things when they turn it on. Main component of natural gas. The bonding inside methane is covalent. They exist as independent molecules. Although the melting point of methane is very low, about 1,000 degrees lower than sodium chloride, the physical property does not affect the strength of the carbon-hydrogen bonds in methane, or indicate that the bonds are weak compared to that of sodium chloride. This is worth highlighting, this is because no chemical bonds are broken when methane or any molecular compound melts. So what attractive force are we overcome? Well, we're overcoming the attractive force between neutral molecules. Water's an example of that. A crystal of ice has all the molecules locked in place. When I melt ice, all I'm doing is overcoming the attractive force between the molecules. I'm not breaking chemical bonds. I'm breaking attractive forces between molecules. Instead, weak intermolecular forces, that means between molecules, are overcome. The result is that molecules are just separated from each other, rather than breaking the chemical bonds between the atoms within the molecules. Now that's not true when I melt an ionic compound. I'm overcoming ionic bonds. I'm not separating the ions physically from each other, I'm not vaporizing it, but when I break a crystal down so that it's liquid, in other words, I turn NaCl solid to NaCl liquid, I have to overcome the ionic bonds holding the crystal together. I don't do that when I melt molecular compounds. All I do is pull the molecules apart. The chemical bonds within the molecules aren't being touched. The energy required to separate the bonded carbon and hydrogen atoms within the molecules from each other is far more than that required to simply pull the molecules apart. In the final section in this chapter, we'll discuss the different forces that actually hold molecules together. We'll talk about 3 or 4 of them. But suffice it to say, when I melt or boil a molecular compound, I'm not breaking chemical bonds. Compelling evidence for the strength of covalent bonds can be seen by studying compounds called network covalent solids. These are the counterpart to ionic crystal lattices. They're covalent compounds, kind of like this, okay? Rather than consisting of individual molecules, these substances are held together by covalent bonds that extend throughout the entire sample. In the same way that melting an ionic solid requires overcoming all of the attractive forces between the oppositely charged ions in the crystal lattice, melting a network covalent solid requires breaking all of the covalent bonds within what is effectively a giant molecule, literally as big as the sample. Quartz is a great example of that. Consider quartz, for example, which is a network covalent solid having the formula SiO2. SiO2 is just the ratio of the atoms in that big covalent compound. And if we grind up quartz into tiny little pieces, we call it sand. But the SiO2 doesn't mean there's a molecule of silicon dioxide. It means the ratio of those atoms in that big network covalent solid is 1 to 2. Even though the bonding is covalent, it doesn't exist as molecules. Most covalent compounds do exist as molecules. But it's incorrect to replace covalent compounds with, or molecular with covalent. Because just because it's covalent doesn't mean it's molecular. If it is molecular, yeah, the bond is covalent. But just because the bonds are covalent doesn't mean it exists as individual molecules. The melting point of quartz is almost twice that of sodium chloride. Sodium chloride's 801, quartz is 1550. And now we're comparing apples to apples. Because when we melt quartz, we are breaking chemical bonds. Just like when we melt ionic solids. Okay? The melting point does reflect the strength of the bonds in the compound. It shows us that chemical bonds can be as strong as ionic bonds. And there's kind of a computer-generated diagram of a quartz crystal, but you can't look at that and identify individual neutral molecules. Okay? So that's why throughout the rest of this section, when it categorizes compounds as molecular, I would prefer you replace it with covalent. Okay? A couple other things. And I hate to correct Gary, and I know he knows this. I just think in his attempt to introduce it and be straightforward or simple, sometimes he blurs the line between correct and incorrect. Nonmetals form covalent compounds with other nonmetals, but form ionic compounds with metals. So let's talk about what is true. Any binary ionic compound has a metal and a non-metal. Okay? You could even say any binary compound starting with a metal is ionic. Any 2-element compound that begins with a metal is an ionic compound. Okay? So any compound containing a metal is an ionic? That's not true. Any binary compound containing a metal is ionic. Even that. Let's fix that. Most binary compounds containing a metal are ionic. Just because, though, it's a metal non-metal doesn't make it ionic. And we have to go a little bit further afield here to explain this. if you look at the back of your book, this periodic table, you see the numbers in the top right-hand corner of each box? Back in Science 10, those were charges, right? Common charges. What's in the key? What's that little number represent? What's that word? Electronegativity. That's another property of elements, and what it tells us is, you don't have to know this yet, but I just want to correct this. Electronegativity is the tendency of an atom in a bond to attract bonded electrons to itself. Every chemical bond begins when the electron clouds of, which are always on the outside, of two elements overlap. And then depending on how much they overlap and depending on, what the elements are involved in that bond, the electrons are either shared or they're transferred. If they're transferred, we form a positive ion and a negative ion, called an ionic bond. An ionic bond has to be between a metal and a non-metal, okay? So an ionic bond always involves a metal and a non-metal. But just because it's a metal and a non-metal doesn't make it ionic. And you might say, well, how? That seems like a contradiction. Not really. Those numbers up there tell us how well each of the atoms in the bond pulls on the electrons between them. And if an atom in a bond pulls electrons between the two nuclei really well towards itself, it's got a high electronegativity. If an atom has a low electronegativity, it means it doesn't pull on bonded electrons very well at all. So, if you look at the periodic table in your back of your book, the lowest electronegativities are over here, which kind of makes sense because metals tend to give their electrons up. And the metal that has the lowest electronegativity is the metal that gives away its electrons easiest. Cesium. We're not going to include francium because it's radioactive. Cesium's electronegativity is 0.7, right? What element in the table wants electrons the most, based on our last class discussion? What's the most reactive element in the table? What's the electronegativity of fluorine? That's the highest in the table. If when a metal and a non-metal get together, if the difference in the electronegativity is more than 1.7, then that means that the metal is so lousy at attracting electrons to itself, and the non-metal is so good at attracting electrons to itself, that for all intents and purposes, the electrons are transferred. The metal loses its outer electron, becomes a positive ion. The non-metal gains that electron, becomes a negative ion. As long as the difference in electronegativity is more than 1.7. If it's not 1.7, if it's not that big, the electrons might be shared, but they're going to be shared unequally. And in grade 10, we talked about ionic and covalent bonds, maybe in grade 9 too. But between ionic, which is electron transfer, and pure sharing, which is covalent, there's a big gray area in the middle called polar covalent, where the sharing is unequal. It's like, I don't know, your little brother out for Halloween and he comes back in his bag of chocolates and you got a big chocolate bar and you tell him you're demanding he shares his chocolates with you because you're too big to go out for Halloween. So you take his chocolate bar and you break like a fraction of an inch off and give it to him. You eat the rest, you can do that because you're big, he's little. Are you sharing? Technically, but not equally, right? So covalent would be breaking it right down the middle. Ionic is, you just take his chocolate bar away and he cries and you keep it, doesn't matter. Unequal sharing is you break a tiny little minuscule chunk of chocolate and give it to him, and then he can't say, well, he took my chocolate bar, he said, no, I shared. Unequal sharing. That's the majority of bonding in the table. So ionic and covalent bonding is an entirely different types of behavior. It's just sharing equally, really unequally, or somewhere in between. At 1.7, chemists speak of percent ionic character as being 51%. In other words, 1.7 is a cutoff. At 1.7, it's more ionic than it is covalent. And greater than 1.7, for all intents and purposes, the electrons have been transferred. So, what's the electronegativity of aluminum? And aluminum's a metal, right? Not a metalloid, a metal. 1.5. What's the electronegativity of sulfur? Non-metal. That difference is only one, isn't it? That bonding isn't ionic. It's unequal sharing. But it's still a metal and non. What's the electronegativity of hydrogen? And oxygen? 3.5. That difference is 1.4. The bonding in water between hydrogen and oxygen, two nonmetals, is closer to being ionic than the bonding in aluminum and sulfur. Metal. Okay? So what do we call the bond if the sharing's unequal? We call it polar covalent. And that's what we're going to talk about in that section in chapter 6. And the only reason I go into it now is because this isn't true. Just because it has a metal in it doesn't make it ionic. Usually it does. Okay? If it's ionic, it has to be a metal non-metal. And if it's a metal, if it's an ionic bond, it has to mean we have something over here with a low electronegativity bonded to something over here with a high electronegativity. And that only happens if it's a metal, if it's a non-metal metal. But just because it's a metal non-metal, as they get closer together, the electronegativities get closer. The lowest electronegativities are over here. That's one of the things we use to classify a metallic property, low electronegativity. The highest electronegativities are over here. And as I think we just demonstrated, the lowest electronegativities are lower left. The highest electronegativities are upper right, which corresponds to the biggest atoms, which give their electrons away, and the smallest atoms, which want. Notice that there's no electronegativity for the known gases. Why? Because it's a property that requires a bond. The definition of electronegativity is the tendency of an atom in a bond to attract bonding electrons to itself. Well, these never form bonds. So you don't define electronegativity. You have to have two atoms connected together. We'll talk about a number of trends when we get to chapter 6, but electronegativity differences, and in chapter 6 we just abbreviate it like that, delta E, okay? That is why this isn't always true. This next one, I don't know, it seems like a contradiction to me. Any compound containing only nonmetals, cross that word out and write, is a covalent compound. We just explained why it's not molecular. And then after he says any, then he goes except compounds containing the ammonium ions, which are ionic. So after saying this, which isn't true, and that should be covalent, then he says, well, except if it's this. So there are lots of ionic compounds that don't have metals at all in them. If you look at that, there's no metals there, right? Yet it's an ion. What about this compound? Ammonium carbonate. No metals at all. So as soon as you recognize polyatomic ions, it's an ionic compound. But I can't find a metal in there, that's ammonium carbonate. And because most of the polyatomic ions have only nonmetals in them, if you've got ammonium stuck to any of those, there's no metals at all, yet it is ionic. Okay? And I don't like this any, all, never, always thing. Because the more you get into chemistry, you more realize that sometimes this is a little nuanced. And nature doesn't like always to be fit into hard and fast categories. Classifying a compound as ionic or covalent. Obviously ionic, and if you want to prove it, look at the two electronegativities. Sodium's 0.9, chlorine's 3.0. That's 2.1, yeah, that's ionic. Fluorine is the most electronegative atom. There's two, the second to fluorine is oxygen, which is 3.5. And then tied for third is chlorine and nitrogen, which is 3.0. Okay? Obviously that's ionic. You got a polyatomic anion in there. Copper 2 nitrate. That's obviously covalent. The formulas that we write for covalent compounds, if they're molecules, don't represent a ratio. They represent the actual number of atoms. And I might have made this point in grade 10. What's that compound? Starts with a G. Glucose, yeah. Obviously, that's not a ratio, right? If it was a ratio, the formula would be this. Right? That's another molecule. That's formaldehyde. That's embalming fluid. We put that in dead bodies. Okay? That's something your brain runs on. They're not the same. A mouthful of that'll kill you. You need this or you die. Okay? Yet, in terms of the ratio, it's 1 to 2 to 1. So molecular compounds, covalent compounds that exist as molecules, the formula doesn't represent a ratio. It represents the actual number of atoms. And then you get into a whole other level of, okay, well, that tells you the atoms are in the molecule, but it doesn't tell you how the atoms are structured. And that's a cool challenge of organic chemistry, is that the formula tells you nothing about how the atoms are stuck together. And sometimes, for the same formula, you can get a whole bunch of different ways the atoms are stuck together, and it's not even the same compound. I hate to go far afield, you have to write this down. Let's C6H12. I'm aware of 38 ways those atoms can connect together, and they're all different compounds. And that's one of the reasons organic chemistry is so complicated. Okay? Carbon can form chains, it can form rings, there's different compounds that actually mirror images of each other, and they're different. And that's, I don't want to spoil it for you, that's coming up on organic chem near the end of the year. Okay? And because covalent compounds that exist as molecules don't represent a ratio, that's why we have to indicate the number of each atom. I can't just call that phosphorus oxide, because there's 2 phosphorus atoms and 5 oxygen atoms in that molecule. So I gotta call it diphosphorus pentoxide. And we'll review naming in section 2.4. Now this is not difficult. Classifying a compound as ionic or covalent. Obviously covalent, ionic, and if you're not sure, just look at the electronegativities. So fluorine and calcium, anytime fluorine's stuck with a metal, it's ionic. It's just got 2 ion electronegativities. That's covalent. Magnesium phosphate, you see a polyatomic ion there. Lithium dichromate, that's ionic. Ammonium chloride, no metals, but it's still ionic, because you see a polyatomic ion. Okay? Not overly challenging. Another way we can classify compounds, and this is worth introducing here, and I like the way Gary, I rarely say that, but I like the way Gary has sort of defined acids here. Acids versus bases versus salts. If you take Chem 12 next year, assuming I'm still here and I teach it, about a third of the year is devoted to acids, bases, and salts, okay? Some compounds are classified as acids, bases, or salts. There are both organic or inorganic acids, bases, and salts. Now, here's 3 common acids. Hydrochloric acid, sulfuric acid, phosphoric acid. At first glance, you might think, okay, well, there's sulfate. That's got to be an ionic compound. There's phosphate's got to be ionic. But the other thing you notice is there's only nonmetals in there. So, from the formula, an acid appears to be a compound having 1 or more hydrogen ions. Yeah. bonded to an anion. In reality, though, acids are actually a special type of molecular compound that can be induced to form ions. Induced means talked into it, convinced. Okay? So what causes these molecules to form ions? Well, usually water. When you add these things to water, to a greater or lesser extent, they come apart as ions. So for example, hydrogen chloride, that's a gas. But when we bubble it into water, 100% of the HCl molecules come apart into hydrogen positive ions and chloride negative ions. Now we call it hydrochloric acid. When I take hydrogen phosphate and put it in the water, only some of the molecules come apart into ions, not all of them. And that is why, as you're going to learn in grade 12, that's a weak acid, and that's a strong acid. Sulfuric acid is another strong acid. You put that in water, it ionizes completely. That's how we determine whether it's going to be a strong acid or a weak acid. So the word strong to weak acid for a chemist is not the same as coffee, strong or weak coffee. Strong or weak coffee or strong or weak tea is concentrated. But concentration has nothing to do with acid strength. It has to do with how well these things ionize. All right? So that's, we'll spend a lot of time talking about acid-base chemistry if you guys choose to take Chem 12 next year and if I haven't retired yet. I might retire, but I don't know yet. It depends how pleasant or unpleasant the remainder of my teaching experience is this 43rd year of my career. Okay? Yeah. Started teaching when I was 26. Now I'm 69. Yeah, that's a long time. And then 5 years as a student. That's 48 years of my life in this school. God, it's way, way too long. I guess it's a cool thing. Maybe it's a creepy thing. I still enjoy the teaching. I still enjoy this. What I don't enjoy is all the other stuff. I don't want to get too politically incorrect, because at least I want to keep my job at least for the rest of this year. Anyway, chemists actually have 3 different conceptual definitions of acids and bases. Don't worry about the 3 definitions. We'll talk about them next year. Maybe. Now, what's a base? Well, a base, this is actually not a bad definition. Base is a hydroxide. If it's a hydroxide, it's ionic. So an ionic hydroxide is a base. And you don't even need the word ionic there, because if it's hydroxide, it is ionic. If you have an OH in an ionic compound, the OH is hydroxide, which makes it a base. Just because the OH is there, though, it doesn't necessarily mean it's ionic. Now, I'm not blaming this one on Gary, but that is not ionic. That's covalent. But this isn't hydroxide. In this compound, this isn't hydroxide. Okay? The compound has to be hydroxide ion. That's methanol. That's an alcohol. Okay? There is OH in it, but the OH that's there isn't hydroxide. Okay? So that's true. If it's hydroxide, if it's OH minus, if it's got the hydroxide ion in it, it's a base. Okay? Now what's a salt? I would like to say, this isn't untrue, but how about a salt is any ionic compound that doesn't have hydrogen ions in it and doesn't have hydroxide ions. Any ionic compound whose positive ion isn't hydrogen and whose negative ion isn't hydroxide. That's a salt. Any ionic compound whose positive ion isn't hydrogen and whose negative ion isn't hydroxide. Now, how do we make a salt? Well, you guys know this from us. And we're going to learn, and we don't really need to write this down yet, but let's say that's our acid. And notice I put AQ there, dissolved in water. If it's just that, that's a gas. Now let's say I react that with a solution of sodium hydroxide. The ions change places. positive ion of the salt, of the base, which is sodium. Exchanges ions for the acid, and the positive ion of the acid, the hydrogen, forms a covalent compound with the base. So neutralization is really just a form of double replacement. The ions change places, okay? So we make a salt by connecting the positive ion of a base to the negative ion of the acid. And what's left? Positive ion that isn't hydrogen, negative ion that isn't hydroxide, and water. Now last year we didn't call this double replacement. Double replacement from last year is you mix two solutions and you get a solid, right? But this is a form of double replacement. It's kind of a subcategory where the ions still change places, except one of the products is ionic, the other one's covalent, right? So you can see there the salt that we produce, positive ions and hydrogen, negative ions and hydroxide, right?
On there it says that a salt is one type of ionic compound, the only other being a base.
Yeah.
Meaning that acid isn't ionic?
Technically, no. It's actually a molecular compound that can be, that forms ions to a greater or lesser extent in water. Yeah. So acids are only ionic when they're in water.
Okay.
So that is the formula for, like, if you name that, that's hydrogen monochloride.
Mm-hmm.
If you put a little AQ after it, now it's ionic. In other words, water has pulled it apart into ions. Okay? It's not, I'm actually glad you asked that, because often this year, we're not gonna really contradict what you learned last year in grade, and even in grade 9. We're just gonna,
Good morning, St. Thomas More. Please excuse this interruption. Could I have, actually, this is the final call for grades 8 to 11. For those students that did not have their picture taken on the first day, or for the students that need to have a retake, please make your way to the office now. Only students, cafeteria. Please make your way, only grade 8s and 11s. And remember to bring your student ID card with you. Thank you.
you see, that's what I mean. Right?
That was only a minute left.
Okay. So we're gonna maybe drill down into simplicity with a little more complicated aspects of things that at first glance, this is a simple way to look at it, but in reality, it's maybe a little more complicated than that. We're gonna do that over and over again this year, okay? Circle the correct response. Salts are ionic. Magnesium hydroxide's a base. Silver bromide's a salt, okay? Now let's go down the other side of the matter map, the mixtures. This won't take us as long. And I don't really have any corrections to make for the mixture components. So if you go down the left-hand side of this one, remember the thing that distinguishes mixtures from pure substances is the components are physically combined. Which means if they're physically combined, I can vary the amounts, and if I can vary the proportions, I can vary the properties. That word vary is not something you can put into a pure substance, okay? If we divide mixtures, we can divide them into homogeneous or heterogeneous. Homogeneous means the same throughout, made of the same. Heterogeneous means made of different. Gary makes a good point here that the distinction, and let's see if we can look at it at the top of the next page, then I'll come back to that table. The differences between the classes of mixtures heterogeneous, homogeneous, solutions, colloids, suspensions, is really a matter of degree rather than of kind. And what is the degree of what? Size, okay? It can't be overemphasized that there is no sharp demarcation, means distinction, between the classes of mixture, but rather a general trend, kind of like a spectrum, from small particles to increasingly larger. And as you go from really small to a little larger, you go from solution to colloid. As you get still larger, you go from colloids to suspensions. All right? So it's really the component size that gives you that continuum. So a homogeneous mixture is one that appears the same throughout. Now don't worry about it's not actually homogeneous, whatever, okay? The particles, and then he goes into Prue, and it's like, I don't know why. We could probably take out 50 pages of what he wrote. A homogeneous mixture, the particles are small enough that you can't see them as being different. They don't appear to be any different. But that's only because of how big they are. And where the components of the mixture are the smallest in a homogeneous system are solutions, okay? A solution is a type of homogeneous mixture in which the constituent chemical species, the components, do not aggregate, that means get together, to form particles bigger than an atom. If it's a homogeneous mixture, they have to be smaller than a micrometer. So if you look over here on the previous page, a homogeneous mixture, the individual particles are smaller than a millionth of a meter. But if the homogeneous mixture is a solution, they're smaller than a billionth of a meter. In other words, not just smaller than this, smaller than a nanometer. As they get larger and larger, a homogeneous mixture becomes a colloid. But we'll start with the smallest component particles. That's a solution, all right? The components of a solution are a solute is usually dissolved in a solvent. A solute is the minor component of the mixture, generally what has been dissolved, and the solvent is the major component, generally what the solute was dissolved in. And the most common example of that is salt water. Salt, table salt, sodium chloride, is a solid solute. The solvent is liquid water. When you dissolve the solute into a solvent, they become the same phase. So a solvent is always one phase. It doesn't have to be a liquid. Air is a solution. Air is a solution where the solvent is actually nitrogen. Nitrogen is about 79% of the air we breathe. Oxygen is one of the solutes. It's the major solvent. Oxygen in the air is about 21%. Then we have trace amounts of argon gas, some carbon dioxide, some water vapor. So there's several solutes in the solvent, nitrogen, by definition, okay? The most common solutions that you guys are familiar with are aqueous solutions, where water is the solvent. So when I write this, that's interpreted as an aqueous solution of sodium chloride. Sodium chloride is the solute, water is the solvent. Sometimes water is called the universal solvent because it is constructed to be able to pull things apart so efficiently. If I want to overcome the attractive force between the ions in this crystal, a couple ways I can do it. I can melt it. I can raise the temperature above 801 degrees Celsius. If I want to pull the ions apart, physically separate them, then I gotta boil them, which takes a much higher temperature. Another way to pull the ions apart is throw it in a glass of water at room temperature. And the salt disappears, the ions come apart. Water has an ability to pull the ions away from each other. Without the water, it's very difficult to do it. But water has, again, a unique construction. We'll go into it in a lot more detail later on in the year. But water is a little bent molecule, okay? And it's bent because there's actually two lone pairs on the oxygen of electrons, okay? Remember the Lewis structures we talked about last year in Science 10? Those pairs of electrons push the hydrogens out into a kind of a tight V. If you look at your table, what's the electronegativity of oxygen? Second only to fluorine, 3.5. The electronegativity of hydrogen is 2.1. Which means that these electrons in this bond are pulled really close to the oxygen. Okay? So the electrons that are pulled really close to the oxygen and these two lone pairs out here in the oxygen means that this end of the molecule is a little bit negative. And chemists have a little symbol for that. It's a lowercase Greek letter delta. You guys are familiar with the capital letter, the triangle. But the lowercase letter looks like a D kind of squashed in the middle. Chemists use that to represent a little bit. So this end of the molecule is a little bit negative, that end of the molecule is a little bit positive. So the hydrogen end's the positive end, the oxygen end's the negative end. So when I throw table salt in water, the negative ends of the water molecule, the oxygen, is going to naturally attract the sodium cations. It's going to surround it and happily stick to it because the sodium ions in that crystal lattice are positive, and the water molecules wrap themselves around the sodium ions, and the attraction of the oxygen ends of the water molecule to the positive ions is actually stronger than the attraction of the ions for each other in the crystal lattice. So the water molecule will surround the sodium ions and pull them away from the crystal. So when sodium chloride dissolves in water, why does the salt look like it disappears? Because all the ions come apart. So the sodium ion is wrapped in that little water shell. We actually call it that. We call it a hydration shell. And the chloride ions, the big green ones, the positive end of the water naturally orients itself around the chloride ions. So that electropositive hydrogen will surround the chloride ions, pulling them away from the sodium ions in the crystal, wrapping that in a little shell. And if water wasn't bent, if the shearing wasn't so unequal, and it didn't have a negative end and a positive end, then life on this planet wouldn't exist. Most of you guys, well, all of you guys, most of what you're made of is water, but it's not pure water. It's a solution of sodium chloride, a little bit of potassium chloride, and if the ions weren't there, mobile, then nerve impulses couldn't flow. Moving my arm right now, moving my jaw, talking, my heart beating, none of that would happen if electrical signals weren't coming from my brain. Those signals have to travel electrically. And were it not for the ions in the solution, the water solution of my body, none of those nerve impulses could travel. How many, you guys aren't in anatomy and physiology 12 yet, right? If you take that, I think they still talk about this in biology 12, talk about active transport, where for a nerve impulse to be transmitted, the concentration of ions on one side and the other side of a neuron has to change. So you'll hear things like the sodium potassium pump, and the body actually expends energy to pump ions across the membrane, and that changes the conductivity of solution and allows nerve impulses to travel. But the ions have to be there. So were water not able to do this, life couldn't exist. And as I've said often, if they're ever looking for evidence of past life on another planet, what's the first thing they look for? Water. Because if water was never there, as far as we know, life couldn't have been there, right? And a lot of people just happily live their life full of water and not knowing how important it is, and how if that angle that it was bent wasn't as small as it was, water would not be able to pull those ions apart. Let's say water was a straight molecule. Let's say instead of being bent, let's say it was like this. Well, now, oxygen pulling on the electrons wouldn't make one end of the molecule any more negative than the other, because those poles would cancel. It has to be bent, otherwise we don't have a negative and a positive end. Okay? And that's, we'll talk about that again. I keep saying it in chapter 6. That's because of the stuff I wrote, but anyway, it's coming up. Did my computer just die? Piece of so the battery's not there. Why did it turn itself off? If it turns itself off, it might not be able to find the internet. That's what I was talking to Mr. Olson about.